Hello, everyone. Good morning. Thanks for sticking around for the Friday session. My name is Jenny Calahan. I'm a postdoc currently at the Origins of Life Initiative at Harvard. And I'm going to tell you something that I started as a grad student and I wrapped up within my first year of the postdoc, which was a small survey with NOEMA looking at some outbursting sources. And the thing that I was most excited about was results from V1057 Cygnus, which I'm really going to highlight. It became my favorite outbursting object. So I was a little disappointed that there was a clear favorite. I think maybe only 2 of us were big fans of V1057 Cygnus. So I'm hoping if you don't take anything else from this talk, you become a bigger fan of V1057 Cygnus. Okay, so why am I interested in studying outbursting sources? We're all interested, of course, but one thing that I find very exciting is that these outbursting sources correspond to a really pivotal and interesting stage in the star-to-planet formation process. They occur in this class 0, 1, maybe 2-ish stage, which also corresponds to when planets we think are starting to form. And these outbursts, not only are they interesting physical mechanisms on their own, but regardless of how they work, they are heating up the inner disk and the envelope, and they're sublimating everything that should be on the ices into the gas phase. So this is a really nice way to get a sneak peek at the volatile reservoir that is available to form planets that we think causes these rings and gaps that we see in class 2 disks. And of course, we also have the big question, what triggers outbursts? We've been talking about this all week. Is it some sort of instability? Is it a flyby? Is it streamers? Is it a little bit of everything? A key parameter, though, that we need to know in order to answer this question is the mass. This has come up a lot in the conference, which is very exciting, so I don't have to motivate why we think the mass is interesting within these sources. But I do want to talk about the way that we calculate mass, because it is difficult. The easiest way and the best way to start with, at least, is to look at the continuum observations and get a flux of the large dust within these disks. And you can use that flux to convert to a mass of the dust population and then convert that into a gas mass if you assume some sort of ratio between the dust and the gas. So you're taking a lot of leaps and bounds to get a final mass. So it would be useful to have a second method to measure mass. And I would like to use gas lines, in particular CO. It's a good mass tracer, especially in this environment where you're sublimating all of your ices. All of the CO should be in the gas phase. So we're finally probing the full extent of the disk and inner envelope. So the design for my survey, I wanted to look at sources that would have detections, as you do when you go out to observe something. So I was looking at the brightest outbursting sources out there that already had some CO observations of some sort that seemed to be peaked on the central source itself. So that left me with 5 sources right here. So we have 3 classic FU Ori objects. We have V1057 Cyg or Ori, and we have V2492 Cygnus. So all very famous sources that have been well observed, that have pretty big outbursts and that are very bright. And so I use NOEMA because NOEMA has a really long baseline, or has a long, is sensitive to a wide range of frequencies, basically. So in one single setup, you can look at 13CO, C18O, C17O, and 13C18O. And so it's a very efficient way to get after the CO towards a source. And I had successful detections of 13CO, C18O, C17O towards all 5 sources, which was really awesome. We can use these observations to calculate optical depth. And so we found that C18O was actually pretty optically thick towards all of these sources. We had to turn towards C17O to get an optically thin gas mass tracer. And we used this as our mass tracer from here on out. And we had 1 detection of 13C18O in V1057 Cygnus. And we also use this to constrain the mass of the source. Here are our continuum observations. So we're seeing disk-like features, maybe a little bit of extra envelope. I think another cool thing, I don't know if I can get this laser to work. Yeah, V1057 we know is a binary, and we see that the continuum peaks where the secondary is, which is kind of fun and good to keep in mind for the rest of the results in this talk. But we also use the continuum to constrain what area that we want to calculate the mass of. So all of these areas contain the vast majority of the continuum flux, and they're also roughly on similar spatial scales, so we can kind of compare these sources to each other. Here are C17O moment zero maps, and so the continuum area that I defined earlier is now in a white contour. So you can see that the C17O is much more complicated. It's probing larger extents, probably a lot of envelope or some sort of inner gas emission that is not necessarily only the disk itself. But I want to calculate the mass just inside of here to try and get the disk alone. And long story short, I'm able to calculate the masses using an assumption that the C17O is optically thin. I also calculate a mass of the dust, as you would for any other normal continuum observation, and multiply that by 100. And so we can compare the masses that you would have gotten from just dust observations to C17O observations. What I'm finding is from the C17O, all of these sources are quite massive, and they are gravitationally unstable with their Toomey Q parameter below 1. Some of these masses that we get from the dust versus the C17O roughly agree with each other, but sometimes they absolutely do not, like V1057 and 2492 Cygnus. I think this means that there's a lot of envelope emission that we're also probing within these small spatial scales. Okay, so those are our mass results. Another very cool thing that popped out of the data as I was cleaning these observations was that one of these sources is not like the other. V1057 is filled with lines. So this is just a small piece of the NOEMA observations that we have. But all the way, we see a ton of lines in this source while we see practically nothing in these other 4 sources. We see our CO lines, of course. We see a hint of formaldehyde over here, maybe a hint of methanol. This is actually a methanol detection. You can't really tell until you zoom in, but it has that line width. It's a very faint methanol detection, but that's it. So it seems like V1057 is quite special amongst these sources. Just taking a inventory of everything we see in V1057, it basically contains everything we would expect to see if this source underwent an outburst and sublimated everything off of the ices into the gas phase. So we see a lot of SO, or we see a lot of sulfur-bearing molecules. We see a lot of what I would call building block complex organic molecules. So we have methanol, we have methyl cyanide, we have formaldehyde and isotopologues of formaldehyde, HC3N. We also have this long COM, this is methyl formate. There are a few other potential detections of COMs that I was not as confident about, but we could always do follow-up observations, and I think there might be more in there. And very excitingly, we have a water detection as well. Just one transition, it's fairly faint, but I was able to calculate a column density for it. And when you look at the moment zero maps for all of these detections, they are all pretty boring. They're just a little unresolved blob, which I think is telling us or suggesting that this is actually coming from the disk itself, not necessarily the envelope. However, for formaldehyde, there is some envelope detection, which we're not too surprised about. Okay, now, the big question for me was, is V1057 actually special amongst these sources, or is it some sort of observational bias? So if we just look at the column density that I derive for the sources that have some detection of methanol, V1057 is really methanol rich. These upper limits here are far below where V1057 is. So that makes it seem like it's kind of special, but of course we need to put that in context with other lines and other information we have about the source. So we have some formaldehyde detections in all of these sources at some extent. And if you take the ratio of the column density from methanol to formaldehyde, V1057 is looking maybe a little bit less special. It could be special, but these are really rough upper limits. There could be some methanol hiding here that makes V1057 look a little bit less unique. And then if you put in context with C17O, our mass tracer, it looks like maybe just V1057. It is our most massive source. It's our brightest source. So it's not too surprising that we're able to see, if there's going to be a source in the sample that's super line rich, it would be V1057. Although it does look fairly unique compared to 2492. The rest, we just don't have enough data to really say if this is unique or not. But the really exciting thing about this is that we can now put this these results in context with other results we have. And so I really like this question that Agnes brought up yesterday during the discussion. There are, I think, still a ton of mysteries of planet formation that can be answered through outbursts. And my answer to this question would be that outbursts, I'm agnostic as to how they outburst, but they are a really convenient way to look at the chemical reservoir available to forming planets. And so we can use outbursts to connect between protostars all the way to comets. And so that's what I'm doing here in this plot. So we have our outbursting sources, V1057, L1551 IRS5, V883 Ori. This is the best sample we have so far. We have some class 2 transition disks. Thank you. Which also are a way to kind of expose the icy reservoir that's available to forming planets. And of course, we have our PILS sources and comets. And so if we just step through these different molecules, these are all ratios of molecules to methanol. And so if we start with water, I don't know if I really see anything here. I don't think there's a clear trend. Although it is kind of peculiar that V1057 here seems to be much more water rich than the other outbursts. I think that's weird. I don't know why. I do think we need follow-up observations to be certain of this, and maybe more observations of other sources to see what is typical. Methyl cyanide, again, not much of a trend. Okay, can't say much. Now, when we get to this complex organic molecule, I may be starting to see a trend. If you squint your eyes, you see an upward trend. So maybe that's telling us that complexity from protostars to comets, it's getting more complex. So that's worth investigating. And then when we get to our sulfur-bearing molecules, SO2, maybe there's a trend, and then OCS, I don't see much of a trend. But this is kind of exciting. I want to see more plots like this. I want to see more data points in here. It's fairly easy to get this information from protostars and comets. You know, you have to go to the comet and measure it, but I would argue fairly easy. And for this transition period, we need to use special objects like outbursting sources to really fill in the gap. Okay, so some of my takeaways. The bright outbursting sources that I saw in this survey appear to be very massive and gravitationally unstable. The molecular signature in V1057 is indicative of an outburst, and it gives us a hint at what the planetary reservoir, or the chemical reservoir, looks like at the start of planet formation. And V1057 is the V883 Ori of the Northern Hemisphere. We need to observe more FU Ori objects to really understand what's going on there. And actually, this project kind of brought up more questions that it answered for me, and so I just wanted to highlight a few of those and what I think is already going on to answer these questions. So first of all, what's up with the water in V1057? Water is just an interesting molecule. I want to understand the water reservoir in protoplanetary disks. And V1057 is giving us a hint that there is a rich water reservoir. Let's further investigate that. And we have approved NOEMA program that is in the queue right now, so keep an eye out for that. Are these sources that appear to be very line rich, are they unique? I don't know. We need more follow-up observations, maybe with ALMA, or deeper NOEMA observations. People are already working on that. Maybe we're doing a community large program. I don't know. I would support that. And then I have a lot of questions about like the sublimation signature. Does it stick around? How long does it take for things to freeze back out? We need more modeling work. And this is actually what I do day to day, is thermochemical modeling. So this is probably the direction I'm going in, but plenty of other people are also working on that as well. So I will end my talk with the takeaways, and thank you all so much for listening.
Thank you very much for this really nice talk. Oh, some people are already.
Thanks for the very interesting talk. So could you explain again how you calculate gas mass to calculate molecule? I think I missed it.
Sorry, I think I missed the last half of that, but just how I calculate the gas mass from like C17O?
Yeah.
Okay, yeah, I assume it's optically thin. I should have put backup slides that had the actual math, but you can see my paper, Calahan et al. 2024. It's fairly simple assumptions, and so you calculate a column density of C17O, assuming it's optically thin. Then you do have to make assumptions backing that out to a CO column density with assumptions of the ratios between 17 oxygen and out to 16 oxygen. And then you'll have to make an assumption of the ratio of CO to H2. So similar to the dust mass, you're making a lot of assumptions, but there are reasons why we're fairly confident about those assumptions. I hope that answered your question.
Yeah, okay, thank you so much.
Yeah, you're welcome.
Next question, Fernando.
So actually, this is a small follow-up to that. How do you get the tumor Q from that?
Oh yeah, so it's I should have added more equations. I'm sorry, but you use the mass and the radius or the emitting region to calculate the tumor Q. I don't remember the equation off the top of my head. I can look it up really quickly. It's in my paper, absolutely. But yeah, I'm using these values to calculate the tumor Q. That's true. That's true. There's a temperature assumption that I believe is coming from the molecules. Yeah, I have measurements of temperature. I'm sure I assumed like 150 or 200, something like that.
Thank you. Next question, Fernando.
For me, it's more of a question / comment. I don't know. In the previous maps where you showed the isotopologues, the different isotopologues, is it maybe because I am tired, but are there streamers in that one? Not in this one. In the other
like
one.
the CO?
Yeah.
Like these or something?
Not in this one.
Oh.
In there are only 3. Yeah, this one.
Okay, so V1057. I want to know that answer too. Okay, so what I did try and make a velocity map to see if there was any sort of constrained movement in a certain spirally direction, and I didn't see it. That was an attempt. I was using better moments. I was using another person's code. I tried my best to pull out some sort of kinematic signature that looked like some sort of spiralish feature. But I think it's possible that there's just there's a dust continuum issue that's like blocking out some emission. Yeah, so I thought so as well when I first saw that, but I'm not convinced that it's a streamer, personally. Yeah.
Next question.
Thanks very much for the very nice presentation. So I wondered, do you have kinematic constraint for the gas mass in the system? It looks like you can do that. So is gas mass look like a few solar mass?
Yeah, that's a good question. That is not something that I've done. You probably could, given the line wing information. We went about trying to get the mass in a few different ways, including using like the optically thin line wings of 13CO and C18O. However, there was a lot of like absorption and other like weird features that didn't seem to be a reliable method either. So we just stuck with this C17O. Yeah.
We have still time for questions. How does that show here?
Hi, thank you so much for the nice talk. I only have a comment about the large programs, and it's a capital yes, please. I think it would be really nice for the community to come together and maybe put in a large program on these sources. I think that would be the best way to do these things. So yes.
Awesome. Thank you. I agree.
Thank you.
Hi, thanks, Jenny. That was really cool. It seems really hard to disentangle these disks from everything else that's going on, right?
Absolutely.
I think I forgot there was some line profiles in there somewhere, but how do the channel maps look? Can you pick out like disk-like behavior, or from the line profiles, can you model those middle bits as a disk, or is it just a mess?
I couldn't get any solid disk emission. I think we're not resolving it. The beam itself is like a few hundred AU, so even in the line profiles, I didn't get any solid evidence of, disk Keplerian structure in there, unfortunately. So we need ALMA. Yeah.
Thank you. Last question.
Dumb question here. Are you able to constrain the strength of the outburst, like the luminosity of the curve? Like, is maybe the one V1057, is it maybe warmer than the others, so it simulates more ices? Are you able to constrain that?
We could constraints on the temperature itself. I'm not getting any constraints on the luminosity of the star itself. I'm using literature values for that.
And those literary values, like, are they different? Like, just those stars,
The
they're
luminosities
different?
of the sources, you're saying? Yes, I have a table of that. V1057 is the brightest, and it's kind of plateauing, so its outburst didn't shoot down like the others. So it is certainly a warmer, denser, more massive source.
Because I'm not surprised, because I would say, like, all those comps, when they sublimate, they are quite refractory, so you need quite high temperature to sublimate them. So I'm not surprised that in this disk you would see more of them.
Yeah.
But we can discuss more after. I like this.
Yeah.
It's an interesting disk. I like it as well now. Thank you.
Yeah, you're so welcome. Yeah, V1057 is really special. Similar to V Ori, it's not only bright, but it's remained bright for a long time. So it's been hot, and it's a larger spatial extent, so it's easier to see in these unresolved observations. So there's a lot of things working for us with this source.
Thank you. Thank you very much. You need to continue it in the coffee break later. We have to go on. Let's thank Jenny again. The next talk will be